Hi guys. Okay, now we move to part 2, chapter 5, magnetic circuit. Okay, learning outcome for this topic. Okay, at the end of the topic, students should be able to discuss the series and parallel element, explain the magnetic circuit with DC excitation, and analyze the magnetic field intensity and magnetization curve. Okay, for series and parallel element, okay, magnetic circuit may have section of different material. For example, the circuit in the following figure has section of cast iron, sheet steel, and air gap. Okay, sheet. So they have three elements in this core. Okay, the circuit. Such a circuit is called a series magnetic circuit. And for parallel element, okay, a circuit may have element in parallel, such as in this figure. Okay, at each junction, the sum of flux entering is equal to the sum leaving. It's same like the KCL or Kirchhoff currents law. Okay, magnetic circuit with DC excitation, basically there are two basic problem to consider for analysis of magnetic circuit with DC excitation. The first one is when the flux is given, so we have to determine the current that required to produce it. Okay, and the second one is when the current is given, so we have to compute the flux produced. So now we will concentrate on the first one, which is when we know the flux and we have to find the current. Okay, for that we have to know every parameter in the magnetic circuit. The first one is MMF, or magnetomotive force. Okay, or F, or in the symbol is F, and the unit is ampere turns. Okay, the formula is F equal to Ni. Okay, the second one is the reluctance. Reluctance is similar to resistance in the electric circuit, but for the magnetic circuit we use reluctance. Okay, the opposition to magnetic flux. Okay, the flux in the magnetic circuit also depend on the opposition that the circuit present to it. Term reluctance depend on the dimension of the core and the material of which it is made. Okay, the symbol is R, okay, and the unit is in ampere turn per Weber. Okay, so like resistance of a wire, reluctance is directly proportional to length or inversely proportional to the cross sectional. In equation, okay, R equal to L over mu A, or F divided by phi. Okay, for formula of reluctance equal to L over mu A, okay, basically mu equal to mu naught times mu R. Mu naught is constant value and mu R equal to 1 for non-magnetic material, but for ferromagnetic material they have value and the value is different. Ferromagnetic material have high permeability and hence low reluctance, while non-magnetic material has low permeability and high reluctance. Okay, Ohm's law for magnetic circuit. Okay, the relation between flux MMF and reluctance is phi equal to F over R. Okay, the flux or the phi is similar like current in electric circuit. Okay, F similar with voltage and reluctance is similar to the resistance. This relationship is similar to Ohm's law and depicted symbolically as follows. Okay, like this. Okay. Okay, now we see example 3. For these figures, okay, we show that the conductor, okay, wound the core, okay, and the number of turns is about 300 turns. Okay, the current inject through this coil is 0.5 amp. Okay, the reluctance of this magnet circuit is 12 times 10 power 4 ampere turn per Weber. So find the flux in the circuit. So this is the solution. We know the F MMF is N time I. Number of turn time current is 150 ampere turns. Then to calculate the flux equal to F divided by reluctance. Then we will get the V value is 12.5 times 10 power of negative 4 Weber. Okay. Magnetic field intensity and magnetization curve. Okay, magnetic field intensity or magnetic strength is H. Is a measure of the MMF per unit length of a circuit. So the formula is H equal to F over L equal to Ni over L. Okay. H is also known as the magnetizing force. So we can rearrange, okay, this formula. Then we will get Ni equal to HL. In electric circuit analogy, Ni product is an MMF source, and while HL is product of MMF drop. Okay, so Ni is similar to the voltage source, and HL is similar to the voltage drop. And for the series circuit, okay, the voltage source equal to the voltage drop. Okay, now we see the relationship between B and H. Okay, the relationship is B equal to mu H. Okay, mu equal to the permeability. Okay, mu equal to mu naught times mu r. Mu naught is the constant value, 4 pi times 10 power of negative 7. And mu r is depend on the core type. And the core type of the mu r of the mu r is different for different type of core. Okay, now we see the magnetization curve or BH curve. Because for the ferromagnetic material, mu is not constant but varies with flux density, and there is no easy way to compute it. So a set of curves called BH curve or magnetization curve provide information about B and H. A separate curve is required for each material. Okay, for here we have 3 type of core: cast iron, cast steel, and sheet steel. So we have 3 type of core. We have different B and H value. Okay, so we have see example 4. For example 4, if B or the flux density is 1.4 Tesla for sheet steel. Okay, this is the curve for sheet steel. So what is the magnetic strength or H? So we refer to the BH curve. Okay, so we know the B and we can find the H. Okay, the value of H is 1000 ampere turn per meter. Okay, this is exercise 2 that you have to answer and submit to the empty assignment. Thank you.